Okay, so let's continue on with part B of our lecture, which is going to cover cardiac muscle histology and electrical activity of the heart. This is going to be one of the more challenging lectures for y'all, unless, of course, you love Chapter 12 from A&P1, which was neurophysiology and electrical physiology of the nervous system. We're going to be reviewing and including a lot of those concepts from Chapter 12 here in cardiac muscle physiology. So if you are a little dusty on those, or rusty on those, I should say, you might want to pause the recording and go review your notes here, because you should be very familiar with the concepts of depolarization, repolarization, refractory period, concentration gradients for sodium, potassium, chloride, what is a voltage-gated channel, ligand-gated channel, etc. You're also probably going to want to make sure you're familiar with autonomic nervous system neurotransmitters and receptors, as those will come up here as well. So again, if you're rusty on any of that, or that all sounded like Greek to you, you're definitely going to want to go review that before continuing on here. Excuse me. Right now, this should be a pretty much review. If we look at our cardiac muscle cell and muscle tissue, some things that are similar and some things that are different from what we saw previously with skeletal muscle. So again, with cardiac muscle, we have this branched-like cell that are interlock here at these points, referred to as intercalated discs. Unlike skeletal muscle, which was a single cell that ran the length of the muscle organ, cardiac muscle does not extend the length of the organ. Instead, it's interlocked together at these intercalated discs. Now, these intercalated discs appear, as you recall, from A&P1 as thick bands under the microscope. Those thick bands originate for multiple reasons. Number one, there are these little papillae here at these junction points, and these allow the muscle cells to interlock with one another much more tightly when we have that interlocking arrangement. In addition to that, we're going to really secure the two cells together with these lovely desmosomes, which, as you recall from A&P1, was the strongest of our cell junctions. And finally, we need to make sure that all of these cells can work together as a unit, as one single organ, which means they need good communication. Now, in skeletal muscle, we didn't need that because it was one single organ along the length, one single cell along the length of the organ. So when it's at one single cell, then you don't need to have communication between cells because it's just one cell. Here, since it's a multitude of cells interlocking together, you need to make sure these cells can communicate quickly and easily. So in addition to the desmosome junctions for strength and preventing these two cells from ripping apart during contraction, we also have our gap junctions that allow for these cells to communicate easily and work as a unit. Now, intracellularly, we see, again, some more similarities and some differences. First of all, I want you to look at these two slides here, these two images. Over here, we have your basic cardiac muscle. And over here, as you recall, was your skeletal muscle. Now, one of the biggest differences is going to be the most obvious is the density of our sarcoplasmic reticulum. Okay? You're going to see that cardiac muscle has a lot less sarcoplasmic reticulum than our skeletal muscle. Now, that sarcoplasmic reticulum, as you recall, was used for what? Well, hopefully you're thinking calcium storage. Now, can you remember what that calcium was used for? Well, if you recall from A&P1, that calcium was used to trigger your muscle contraction. It went down and bound to your troponin, which moved your tropomyosin and exposed our binding sites. So the calcium was the trigger. The calcium was the on-off switch for muscle contractions. And that functionality is the same here in cardiac muscle. Now, but here's the thing. Cardiac muscle has less intracellular calcium, less stored calcium inside of the cell. Does that mean it just doesn't need as much calcium? No, it needs the exact same amount of calcium because, as you see, we have the same sarcomeric arrangement. We have the same overlapping actin and myosin and that same functionality. But if we don't have enough calcium inside of the cell, what are we going to do? Well, because we have less stored calcium inside the cell, it's going to require the influx of calcium from the extracellular fluid. Remember, ECF stands for extracellular fluid. Okay, so this becomes important, but what this allows us to be able to do is actually control the strength of contraction for cardiac muscle to a certain degree. Because if we control the amount of calcium coming in from the extracellular fluid, from the ECF, then we can control the strength of a contraction. Now that was not a capability with skeletal muscle, since all the calcium was inside of the cell. We couldn't control its availability. Okay. So this availability of calcium is going to be useful later on when we want to control the strength of our cardiac contractions, or what's referred to as contractility. Okay. Now we also see that the T-tubules are larger in diameter than the in cardiac muscle when compared to skeletal muscle. Can we think of why that might be? Well, let's think about it. Does anybody remember the function of your T-tubules? Well, let's go ahead and draw our muscle cell, right? Now, if you recall from AMP1, that's actually not what I want. The T-tubules serve the purpose to allow the action potential to travel into the muscle cell's interior. This became important because, get my drawing right, action potentials are normally restricted to the surface of a cell. Okay, now if we compare this arrangement with our T-tubules here, so these are T-tubules, okay, compared to, I don't know why that disappeared, there we go, compared to a cell that doesn't have T-tubules. Well, in our original functionality of T-tubules, your action potential, which it occurs when ions move across the cell membrane, okay, if we didn't have T-tubules, the action potential would stay only on the outer surface, and only this outer region of the cell would get the signal to contract, which means any structure, any myofibrils, any sarcomeres in this inner area would lay useless. That, of course, is not something that's beneficial to us. We want to make sure the entire muscle cell gets the signal to contract. So we need a way of bringing this action potential into the central region. But remember, action potentials only occur on cell membranes. Well, that's where the T-tubules come into play. Remember, the T-tubules are invaginations or tunnels of the side of the cell membrane that extend into the cell. So in the presence of T-tubules, action potentials can now travel across the surface of the cell, but they can also go into these T-tubules. And up here and up here. Now this means not only this outer area is getting the signal to contract, but this inner area is getting the signal to contract as well. So that was our original function of T-tubules. But remember, this was in skeletal muscle. Well, we have a similar problem in cardiac muscle now. Not only do we need to deliver that action potential into the center of the cell, let's go ahead and erase. Remember, we also need to deliver calcium. Well, calcium's coming from the extracellular fluid. Well, if we only let calcium in from the outside like this, we have the same exact problem. The only parts of the cell that are going to get the calcium are these outer parts, leaving this big center not receiving any calcium and as a result not being able to contract. So again, with these T-tubules, they not only function to deliver action potential throughout inner parts of the cell, okay, but it also, since it's filled, since T-tubules are filled with extracellular fluid, they also help with calcium delivery to the inner parts of the cell. Now, because of this new function here, that is why the T-tubules have the larger size. So here we see the large diameter T-tubules is an artifact of the need for the extracellular fluid that's filled in that area to serve for calcium delivery. And although those two things are different, overall, the arrangement of the myofilaments, the arrangement of the actin and myosin, how they overlap to form the sarcomere is the same between cardiac and skeletal muscle. As such, the actual contraction mechanism where the actin binds to the myosin, the actin heads bend, the sarcomere shortens, that same mechanism of contraction is the same. That slide is not where it's supposed to be, so let me go ahead and pause the lecture here for a moment so I can correct that. So this slide was supposed to be next, so let's go ahead and continue with some differences in the physiology of the heart and how the heart actually beats. Now, one of the things, let's go ahead and go to a weight screen on this. One of the things you all should remember that's unique about the heart is the fact that the heart can beat on its own. Okay. Now, when we say the heart can beat on its own, what we mean by that is we're saying the heart can contract on its own. Now, as you recall from AMP1, in order for a muscle to contract, it needs to receive an action potential, right? Well, if the heart can contract on its own, that must mean it's able to create its own action potentials. Now, let's do a quick review from AMP1 with, an action potential and what it actually is, since, we kind of need to know this stuff. So we're going to go ahead and draw our graph, and we have a 0, and we have down here, we're typically around -70, and then we have some kind of stimulus that's going to cause our resting membrane potential to rise up, hopefully reaching this magic number of -55, which hopefully you should have the word threshold popping into your head. If we reach threshold, we are going to fire off an action potential up to about +30, and then we're going to undergo the remaining components of our phase back down to resting. Remembering that this phase was our depolarizing phase, which was primarily due to, hopefully this is all review to you, okay, sodium going into the cell, and this was our repolarizing phase due to potassium leaving the cell. Now here's the thing. Action potentials, as you recall, obey the all or nothing principle. The all or nothing principle stated that action potentials either happened or they didn't. There was no in between. And whether or not an action potential occurred was entirely dependent on one simple thing, and that is whether or not you reached threshold. If you reach threshold, you fire. If you don't reach threshold, you don't fire. Well, what that then means is that if we are able to create our own action potential, the only thing we need to do, thanks to this all or nothing principle, is that we need to make the cells, or the heart itself, the heart cells, reach threshold on their own. As long as they reach threshold on their own, everything else will automatically happen. Now, this ability to create its own action potential and to control the electrical activity of the heart is not actually associated with all aspects of the heart. This ability to create action potentials is specific to a small portion of cardiac tissue, about 1% of cardiac tissue called your autorhythmic cells. Okay, the autorhythmic cells create their own action potential, and this action potential, so these guys are going to create the action potential that eventually will trigger the 99% of cardiac contractile cells, so the guys that are actually going to contract and make the heart beat, to contract. Okay. So again, it's this 1% of the autorhythmic cells that will create the action potential that then triggers the remaining 99% of contractile cells, the cells that actually do the contracting and do the contracting and to actually trigger them to work, okay, to contract. So now that we've reviewed all that, you should have a big question in your head. So let's go ahead and clean up some of this stuff, and let's see if we can solve this question. You know what, let me go to a different screen here, and we can continue on. So here we have our big question, and that is, how does the heart reach threshold spontaneously? Spontaneously meaning on its own. Okay. How does this occur? Well, this occurs primarily because these autorhythmic cells, okay, put that in there. Autorhythmic cells possess specialized voltage-gated cation channels that allow for this to occur. And these special voltage-gated cation channels are referred to as pacemaker channels. Well, let's do a little bit of reviewing here. So the fact that they are gated, what does that mean? Well, gated means that they can open and close, and they have an open state and a closed state. Cation channel, what does that mean? Well, technically it means it allows any positively charged ion through it, but the primary ion that's going to be going through it is going to be our calcium. Now tell me, where does calcium want to go? If I open a door in a cell membrane for calcium, does calcium want to go into the cell, or does it want to go out of the cell? Well, hopefully you're thinking that it wants to go into the cell. Which means, if I allow calcium to enter a cell, is this going to cause depolarization or repolarization? Well, hopefully you are thinking a depolarization. Okay, so when these voltage-gated channels are open, we're stimulating depolarization. When they're closed, we're stimulating. We're not having depolarization. Finally, we're going to talk about this whole idea of voltage-gated. That means it's some kind of change in voltage that will open and close them. Now you remember in ANP1, the change in voltage was reaching threshold. It's going to be different here. So what we see is that your voltage-gated channels or pacemaker channels are open when the cell membrane is below threshold. Now this is opposite of what we learned in ANP1. In ANP1, the voltage-gated channels you talked about were closed when you're below threshold. So this is opposite. This is a new frame of thought. Okay? And then the pacemaker channels are closed when we are above threshold. So how does this work? So we're going to say that this is our negative 55 right here, and our membrane is down here at negative 70. So I'm down here at negative 70, which means I am below threshold. And if I am below threshold, that means my pacemaker channels are open, which means calcium is going into the cell. Well, if calcium is going into the cell, am I going to stay at negative 70? Hopefully you're thinking, no, I'm going to begin to rise up. Oh, I reached threshold. Now I'm above threshold. That means my pacemaker channels are going to close. But do I care? You should be saying no, because if I reach threshold, I'm firing off. Oh, back below threshold. My pacemaker channels are going to open. Calcium comes in. Oh, I'm above threshold. My pacemaker channels close. But I don't care because I've reached threshold and I've fired. Oh, back below threshold. My pacemaker channels are going to open. I'm going to begin to depolarize again. Oh, threshold. They're going to close. But I don't care because I've already reached threshold and I have fired off. And this continues, so on and so forth, never ending until you die. What we see here, what we set up, is a completely repeating. So this creates an automatic repeating series of action potentials. Again, this sets up a situation where the heart creates an automatic, a series of automatic repeating action potentials. Now, this occurs we're going to switch back to my other lecture here. So this occurs spontaneously and in a rhythmic action. And this is due entirely to the heart. The heart does not need any neural input. Which means I could cut every single nerve to the heart and it would still function. So again, I could cut every single nerve to the heart and it would function. Now with that being said, okay, this base rhythm set by the heart fires action potentials about 100 action potentials a minute. So the base rhythm set by the heart is about 100 action potentials a minute. Does that sound right, though? I don't know about you, but it sounds a little fast. If you took your pulse right now, it definitely shouldn't be 100, unless you just, of course, got off the bike. Well, not only that, would 100 potentials be suitable for all activities in our life? So 100 action potentials and 100 beats per minute, is that going to be suitable for all activities in our life? No, if I'm sleeping, I don't want my heart racing at 100, and vice versa. If I'm running from a bear, I maybe want a little bit higher than 100. Well, how can we do that? I mean, the heart can't really know when you're sleeping or running from a bear, right? It's not a brain, it's simply a heart. So how do we do that? Well, what we see is although the heart sets its base rhythm, it can be modified by both neural and hormonal signals. Again, although the heart sets its own base rhythm, it can be modified by signals from the autonomic nervous system and or hormones. Well, how does this autonomic nervous system do the modification? So let's take a closer look. First, let's go ahead and revisit our white screen. Let's go back to a different color here. So as you recall, when we draw this a little bit bigger, I'll try for a little bit straighter line, although I don't know how possible that will be. Slightly better. We have our 0, our plus 30 up here, our negative 55, and our negative 70. Now at rest, we are down here. Go ahead and draw our line across and draw our negative 55 like we had previously. Okay. Now at rest, we are down here, and we are below threshold, okay? Which means we are going to go ahead and open up our pacemaker channels, and we're going to let calcium come in. We're going to have this slow depolarization to threshold. Now, a new term that you're going to learn is this change in voltage. Go ahead and write this down here. A. This change in voltage that is due to the pacemaker channels is referred to as your pacemaker potential. Now again, this pacemaker channel, this change in voltage due to your pacemaker channel is due to your, or is called your pacemaker potential. Now, under normal circumstances, we're going to reach threshold and we're going to fire off. And we're going to come back down, and this is of course going to repeat. Now, as we said, this 100 action potentials a minute maybe isn't sufficient for all activities in our body. Let's say we're running from a bear. We probably want to speed this up. Well, if we want to tell the heart to speed up, we want to use signals from the autonomic nervous system. But what division of the autonomic nervous system do you think we're going to use with our running from a bear situation? Well, hopefully you are thinking the sympathetic nervous system. So we're going to use signals from the sympathetic nervous system to speed up the heart rate. But the question is, how are we going to do that? Well, remember, action potentials obey the all or nothing principle. Well, if they're obeying this all or nothing principle, that means if we're going to create an action potential, we're going to create an action potential, and it is going to fire at 100% every single time. Which means the amount of time it takes to complete this action potential, is it ever going to change? If it's all or nothing, no. We can't make it occur faster or make it occur slower because it's all or nothing. It either all happens or it all doesn't. So this time period is fixed. So the action potential time frame is fixed. Now, what isn't fixed, however, what isn't fixed is the time it takes to reach threshold. We can manipulate that all we want because that is not part of the action potential process. Now, if we want to reach threshold faster, or if we want to speed up our heart rate, well, we need to reach, that's not actually the color I want. Let's go ahead and go back to this color. There we go. We need to reach threshold faster. Because if we reach threshold faster, we're going to fire action potentials much more frequently. But again, how do we do that? Well, let's go ahead and clean this up a minute and see if we can figure that out. Well, under normal circumstances, when this pacemaker channel is open, we are going to reach threshold in, let's say, we'll say that's 10 milliseconds. I am just throwing numbers out here for demonstration purposes. These are not accurate. It's just for demonstration and comparison purposes. So just want to make that clear here. Now, we're going to reach threshold in 10 milliseconds because our pacemaker channels are allowing in 10 positive ions. Well, if we want to reach threshold faster, well, we can't do that with just 10 positive ions. We need to add to that. We need more positive ions coming into the cell in order to reach threshold faster. Well, how do we do that? How do we let more positive ions into the cell? Well, do we just open up more pacemaker channels? Well, no, we can't do that because if we're below threshold, all of our pacemaker channels should already be open. Well, instead, let's open up a channel that's specific to the sympathetic nervous system and allow in more positives that way. That's exactly what we do. What we end up doing is we open up an additional channel that lets in 5 more positives. And now with the 5 more positives plus the 10 we're letting in, we're going to reach threshold in half the time. So how do we do this? Well, taking a closer look, what we see is that sympathetic signaling occurs or causes us to reach threshold faster. Well, how does this occur? Well, as you recall, the sympathetic nervous system releases the neurotransmitter norepinephrine. This is where that review I told you about from the autonomic nervous system is going to come into handy. So this norepinephrine is released from cardiac accelerator nerves This norepinephrine is going to bind to beta-1 receptors. As you recall, beta-1s, the 1s means it's excitatory. Well, what positive do you think we're going to let in here? Well, technically it could be calcium, it could be sodium, but in this case we're going to use sodium. Okay, so this increases the binding, the opened, let me try this, opened beta-1 receptors is going to increase sodium permeability into the cell. And what we find is the added positives entering the cell causes the cell to reach threshold faster. Okay, so this is how the sympathetic nervous system will speed up the time it takes for the cell the cell to reach threshold, and as a result, increase the frequency of action potential and increase your overall heart rate. Now this is great if you're running from a bear, but what happens if you're sitting on the couch doing absolutely nothing? Well, let's how do we then slow down our heart rate to facilitate situations when we're sleeping or resting? Well, if the sympathetic nervous system, let's go ahead and erase. If the sympathetic nervous system, let me see if it's quicker if I do it this way. If the sympathetic nervous system is going to speed up your heart rate, then the parasympathetic nervous system will slow it down. The question again is, how? Let's go ahead and pick a different color and see if we can figure it out. So now we have the parasympathetic nervous system is going to decrease your heart rate. And to do that, we need to slow down how long it takes to reach threshold. So we need it to take longer to reach threshold. Let's go ahead and write it that way. So it must take longer to reach threshold. Okay, now how do we do that? Well, again, if 10 positives cause us to reach threshold in this amount of time, in 10 milliseconds, but we don't want to reach threshold until way over here, then we only need 5 positives coming in. How do we do that? Well, here's the thing. Can we just close off some pacemaker channels? Well, if we're below threshold, we can't do anything with those pacemaker channels. We are stuck with them. So if we have 10 positives coming in through pacemaker channels, and we are stuck with 10 positives coming in through pacemaker channels, we can't do anything with those. Just like you really can't do anything with most of your bills. Okay? The only thing you can do is try to find a way to make those bills less painful. Say by getting another job, or maybe getting rid of some of your cable service. No more HBO for the kids. Well, how does our heart do that? Well, we've got 2 options. Okay? We're stuck with those 10 positives, but option 1 is, let's say we let in some negatives. So at the same time we have 10 positives coming in, we let in 5 negative ions. Well, 10 positives, 5 negatives, that means net only 5 comes in. 5 positives come in, and we've hit our goal. There's another option, though. What if at the same time we let 10 in, we actually at the same time let 5 positives out? Again, with 10 coming in but 5 going out, same principle. We have a net 5 positives in, and we've again reached our goal. This option here is exactly what the parasympathetic nervous system does. Okay, so again, as you recall, the parasympathetic nervous system is going to release ACH. So we're going to have ACH, acetylcholine, from the vagus nerve, binds to muscarinic receptors, okay. This results in, let me rephrase, okay, opened channels increases outward potassium permeability so and this causes, so the positives that are leaving the cell causes cell to reach threshold more slowly. And this is what causes your heart rate to decrease. Now this is exactly what I'm saying here. So here we have our base rhythm. This is your pacemaker potential here. We can speed up, right? Look at that's much shorter. Okay, this is much longer. So again, to review, the sympathetic nervous system enhances or adds to your pacemaker channel. It's going to add to your pacemaker channel when norepinephrine binds to our beta-1 receptors, increasing sodium permeability. The extra positives adds to your pacemaker potential, and we reach threshold more quickly. Parasympathetic, on the other hand, fights your pacemaker potential. Okay, it does this when acetylcholine binds to muscarinic receptors, which increases outward potassium permeability. The positives that are leaving the cell take away some of the positives from the pacemaker potential, causing it to reach threshold more slowly. Remember, this is simply a modification. Okay, the heart is making its own action potential. The autonomic nervous system is simply modifying it. So let's see how well you guys understand with some questions. So pause the recording and see what you come up with. Well, pacemaker channels are primarily, now remember I said they were a cation channel, but I also said that although they're a cation channel, mainly one ion goes through them. And that one ion that goes through them is going to be calcium. Pacemaker channels open. So when do we see their doors open? So read this, take a chance, see what you come up with. Okay, well, pacemaker channels are open when the membrane is below threshold, because remember the goal of these guys is to make the cell reach threshold. Well, if you've already reached threshold, then there's no point in using pacemaker channels, so that doesn't need it. And we, of course, know that these two can't be true because the heart does its own thing without the need for the nervous system or hormones. So B is the correct answer. Here we got a tough one. The autonomic nervous system initiates the contraction of the heart. Well, some of y'all hate true and false statements, but most of y'all that hate true and false statements hate them because you overthink it. Okay? But just as some clarification here for those of you who are a little confused, initiates might be a new word for some of you. So let's just change initiates to starts and see if that helps. Well, remember, the heart is completely autorhythmic. Does not require any signaling, which means this is a false statement. Acetylcholine, what does it do? Notice the double asterisks? So 2 correct answers. So take a second and read through and see what you come up with. Pause if necessary. Okay, acetylcholine binds to beta-1 or binds to muscarinic? Well, hopefully you're thinking muscarinic receptors. And if we are acetylcholine, are we parasympathetic or sympathetic? Well, hopefully you're thinking parasympathetic, which means we want to increase potassium permeability, both of which, or I should say, which will slow down your heart rate. Okay, we will go ahead and stop there. We will pick up with the second component of the electroactivity of the heart and the conduction system with the next lecture.